How's everybody doing? Hope everybody's okay. Just a little side note here. By chance, did any of you guys get a chance to see the lights in the sky last night? The Starlink. I got a chance to see them about 9 o'clock or so. So my background is one of the pictures I took. You see it all lit up. Pretty interesting. Okay. All right. So there is, you can do a Starlink. I think you just search Starlink. They can give you times. I think it's coming up again, at least in our area, in a few more days. So you might do. They'll tell you when it's visible from our area. So it was pretty slick. Yeah. Okay. Anyway, let's continue. I'm going to share with you the schedule that we have because basically today's chapter is very short, and we'll finish it up. And so today is the 6th. We'll finish it up. If I need a little extra time, we'll continue on Tuesday, but I probably not. Don't forget the exam. The last exam, number 5, is on Tuesday, covering chapters 13 to 15. And then next, we'll have a study day 2 on the 11th, and for sure, 13th, which will be the last Zoom time, which will be another study day, and get you ready for any questions because the final exam, which is comprehensive, chapters 1 through 15, is on the following Tuesday, on the 18th. Okay, there is a practice exam on the website, so you may want to look through that to help you out. It's generally consists of roughly about 60 questions. Um, Majority would be multiple choice questions. And once you're done, I will have everything graded that still needs to be graded by then. And the grades will be posted shortly thereafter. Okay. All right. Any questions about that? May 15th. You were saying about May 15th. Oh, May 15th. Yeah, I got you. Yeah, you should. Yeah, you can get online. You can see the Starlink. That is a fascinating thing to watch. I got a little movie on it, but I couldn't upload. I just uploaded my pictures. It's pretty slick. Also, there is an app that you can track the International Space Station, and that's something pretty pretty interesting to watch too as it comes over the skies. Okay, well, let's jump into the last chapter, and we'll talk about solutions. And I got a little cup of coffee sitting there, okay, because that's what it is. It's a solution. Now, most of the time, we tend to think solutions are just liquid, but that's not the case. We're going to learn that solutions can be a combination of gases and even metals. Okay, so what is a solution? A solution, by definition, is a solute, or we classify name as solute, dissolved in a solvent. Okay, and normally the solute is present in the smaller amount. Now, yes, the majority of the time we do talk about liquids, so we say solvent here, but it could be an alloy, metal alloy, for example. We'll talk about that here in some examples. But most of the time, it's an aqueous solution. Doesn't have to be aqueous solutions. It could be a non-aqueous solution. It could be an oil solution. And so we're going to talk about things that dissolve in water, things that dissolve in soil, and then we're going to know that what it would dissolve in, what a chemical would dissolve in, or a molecule would dissolve in, based on what? Guess what? Polarity. Our last chapter dealt with IMF. IMF, to figure out what IMF we needed to determine the polarity of the molecule. And once we know the polarity of the molecule, then we can all these IMF interactions, but one more property, which would be, is it soluble, more soluble in a water, which is very polar, or is it more soluble in a oil-based solvent, which is non-polar? Okay. So obviously concentrations, it's pretty self-explanatory. A solution here of this could be any color solution. You can see in the far left, very light pink color, not as concentrated, and all the way to the right with more depth color, a more concentrated solutions. This basically says that as we increase the concentration, we are increasing the solute, like making a cup of coffee, making a cup of iced tea or a glass of iced tea. You want it more sweet. What do? We make it more concentrated with sugar, right? Nothing complicated here. That's all it's saying. Now, the different types of material. For example, a solution could be a gas in a liquid. Okay. And obviously, carbonated soda drinks are a good example of a gas, carbon dioxide, which has been bubbled into a solution. Most of the time, water. But there's other gases besides just carbon dioxide, but oxygen and so forth. Fish need oxygen, and if the water has very little oxygen, the fish are going to have a little bit of trouble. You could have a liquid in a liquid. Yeah, a mixed drink, for example, where you have an alcohol and a aqueous solution. That is a solution. Okay, the solute here being the alcohol and the solvent being the water or the time. You could have a solid in a liquid if, in fact, the solid is soluble in solution. And so, and even if it isn't, it could be, insoluble, which means that not as much of the solid goes into solution. So you can have something like salt water. Throw a little salt in some water, the salt dissolves and you're good to go and you got a solution. You can have a gas in a gas. You have our air around us, which consists of a variety of different gases, mostly nitrogen and oxygen, and all kinds of traces of different types of dust. Okay, you can have a solution could be a solid in a solid, and an example of that would be steel, which is a combination of iron and carbon. Pure steel in itself is very soft. It would not function very well to build buildings because of the strength. So what happens is you introduce trace amounts of other material like carbon, which changes the properties, the physical properties, and makes it very strong. Another example is copper. Copper, pure 100% copper is very, very soft. And so is gold. Pure 100% gold is very soft, and by themselves would not function well to make jewelry, for example, with gold or copper plates or copper tubing. You have to add other things to it to give it a little more strength so they can function a little bit better. And those we call alloys. Now, we talk about polarity, and thing to remember is like dissolves like. Polar solutes will dissolve in polar solvents. Okay. Classical example of a polar and a nonpolar is Italian dressing. You have two layers. You have an oil layer and an aqueous layer. They don't mix. And when you get ready to use it, you shake it up and it just form a temporary emulsion. You can put it on your salad, but once you let that bottle sit, you get it totally separated because the oil is very nonpolar and the water obviously is very polar, and they're not going to mix. So polar solvents dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. Okay. Light dissolves light. Obviously, we know that we've seen examples. I just used the example of the Italian dressing, but you may have seen pictures of oil spills. Oil is a very nonpolar material, and the ocean obviously is very polar with the water, and the two don't mix, and we have a problem there when we get oil spills. Now, when we talk about whether something is soluble, we tend to use the term soluble whether it's a solid or a liquid, but there is a little bit of distinction. For example, when we have two liquids that mix, that term used to describe that they mix is called miscible. Okay. If they don't mix because of differences in polarity, then it's called immiscible. Okay. It is when we have a solid in the liquid that we use the term soluble. And so if you have a salt that's defined as soluble, it's soluble. If it's not soluble, it is insoluble. But only when we have a solid and a liquid. Two liquids, you use the term miscible or immiscible. Okay. And that's what I just explained here. And that's defined by the solubility rules, whether something is soluble and insoluble, but you're dealing with a solid and a liquid. Okay. So what we have here is a table. Okay. And they're asking you to determine whether the solute, which is up here in the top axis, whether these solutes will the solutes all right here, okay, whether they will dissolve in these particular solvents, okay. Well, keep it in mind, like dissolves like. So the first thing we have to do is determine the polarity of everybody, because once we know the polarity, then we know whether it will dissolve in each other. Okay, keep it in mind, like dissolves like. Now we talked at length about hydrochloric acid. Hydrochloric acid is polar, and so is ammonia. Remember, we wrote this. We determined the Lewis-Dot structure of ammonia. Nitrogen has a lone pair. Automatically think polar. So ammonia is polar. Okay. I think I'm going down the solvent column first. The next one, C12H26. You might say, well, I don't know what that is. Okay, that's all right. Structurally, you may not know what it is, but do recognize the fact that all you see is carbon and hydrogen. That's it. The structure is not really important at this point in time. And so having nothing but carbon and hydrogen tells you have a nonpolar solvent. And then bromine, diatomic, okay? All diatomics are by definition nonpolar because the electronegativity of both the bromines are the same. So there's an equal sharing. So we define the polarity of the solvents, and the next thing we need to do is define the polarity of the solutes. Hydrochloric acid, we have a hydrogen bonded to chloride. Polar compound. It's covalent, but it's very polar. We have two different elements being bonded together. Automatically polar solid. Okay. H2, iodine. Just like bromine, it is diatomic, and diatomic tells us nonpolar. PCl3, phosphorus trichloride. Okay. If we do Lewis-Dot structure here, we end up like ammonia with let me draw it real quick. So do the Lewis-Dot structure and you end up with this type of structure. You're there, and you have lone pairs sitting on the chlorides, okay? And very similar to the structure of ammonia. Difference being that the hydrogens here do not have extra electrons on them. And so both of them share the general formula. Not only that, but guess what? Lone pair in the central atom. Okay. And we have AB3E is the general formula. Okay. Give me 1 second. I'm back. I was having a sneezing fit for some reason. Okay, so that being the case, let me clear the PCl3 is polar. And then we have the solute with carbon and hydrogen. Again, nothing but carbon and hydrogen. This is, to recall, this is methane, 1 carbon, 4 hydrogens, tetrahedral, all carbon hydrogen bonds, which are nonpolar bonds. Therefore, we have nonpolar species. Okay. And so now that we have this, we just have to figure out yay or nay. Okay. And yes, for the combination of ammonia and solute, because both are polar. Okay. Nay or no for iodine and ammonia, again, because iodine is nonpolar and ammonia is polar. So they will not dissolve, they just sit there. You know, yes, for trichloro phosphorus trichloride, okay, and ammonia because of the polarity, and then no for the hydrocarbon methane, CH4, and NH3. The next solvent would be no with hydrochloric acid because, again, the polarity difference, two different species. Yes, for iodine, definitely will dissolve because both of them are nonpolar. And PCl3 and the hydrocarbon, that will be a no because the differences in polarity, and a yes for the methane and the C12H26, again, because of polarity. Bromine, no. And for HCl, yes for iodine, no for PCl3, and yes for the methane, again with polarity. So remember, first step, you got chemicals, determine the polarity of them, either polar or nonpolar. And that itself, keep in mind, like dissolves like. And so if they're polar, they will dissolve. Both of them are polar. If they're both nonpolar, both of them will dissolve. Any combination of the other, no dissolving. Another example, you might think about it. I know makeup has changed quite a bit, I'm told, but I remember growing up with five sisters. Every night they had to use an oil base, and probably you still do. You can enlighten me on this. Oil base cleanser to remove the makeup because there's some makeup out there that's pretty hurricane proof makeup. In other words, you got hit by water, it wouldn't dissolve because the makeup was had a lot of non-polar character. In water being polar, they will not mix. Okay. And vice versa, if you had another makeup that was, cheap makeup, or not necessarily cheap, but more polar based makeup, then water would be used to remove it. But same is true with tears. Tears will remove it. So anyway, that gives you an idea about, how you think about the polarity and the like dissolves like. Okay. All right. So when we talk about miscible, immiscible, soluble, and insoluble, remember miscible and immiscible, we're talking about two solvents. So we got a polar solvent and a polar liquid. They will be miscible, just simply again, because there's two liquids and the polarity matches. They will be classified as immiscible, again, because the differences in polarity between the two liquids, immiscible between nonpolar liquid and polar solvent because of the polarity, and miscible because of the common polarity of the two, the liquid and the solvent. Soluble, okay, because we're dealing with a polar solvent and a polar, excuse me, a polar solid and a polar solvent, which is defined as soluble and insoluble if it's a nonpolar solid. A good example would be if you take table salt and let's say you put some butter in the pan to cook up some eggs and you throw salt in there, the salt stays in there. It doesn't dissolve. Okay, because the differences in polarity, sodium chloride is extremely polar, it's ionic. But if you try water, you heat it up in that pan, you throw some salt, guess what? The sodium chloride does dissolve. Nonpolar solvent and polar solvent, insoluble because of the differences in polarity, and soluble again because of similarity of the polarity. Ionic compound and polar solvent, it depends on the solubility rules. Okay. So an ionic compound, metal, non-metal combination, sodium chloride and water, yes, it's soluble because it is, yeah, soluble in water as defined by the rules. And if it's insoluble, remember, it doesn't mean that it's 100% insoluble. It just means that there's a very little amount of ions in solution. Okay, but it does still dissolve some of that material. And then insoluble, if you're dealing with an ionic compound and nonpolar solvent, sodium chloride and butter is, in the pan trying to get that to work. It won't dissolve. Okay. The dissolving process, we kind of touched on this a while back, but basically you have a sodium ion. This is the ion dipole interaction force, the ion dipole, and you can see we got sodium in here, and then we got the polarity or the partial negatives of the water molecule that are interacting with the ion. And if we had the chloride would be over here if this was sodium chloride, and that would be interacting in that with the hydrogen partial positive side of water. Okay. Now, when we talk about concentration, there's two types of concentration that we're going to work with. One is called the mass percent, and that is the weight of the solute divided by the total weight of the solution. Okay, we'll get some examples. And another type of concentration unit that we have is called molarity. Now that deals with determining the moles of material, the moles of solute divided by the volume that you dissolve the solute in. Okay. And so to figure out the moles, remember we start off with grams. If we go to moles, we need the molar mass of that material. Okay. All right. So let's do this. Let's work on the mass percent. Now, how does that define? Well, as I mentioned earlier, mass percent is simply the mass of the solute divided by the mass of the solution. Remember, the mass, 1 second, please. Okay. My apologies, I'm back. Okay, so if we look at the equation, you can see that the solution is the mass of my solvent and the mass of my solute. Okay. Sometimes in these calculations, people tend to forget to include the mass of the solute. And they have the mass of the solvent, but they forget to add the mass of the solute. So, for example, they're asking you here, yeah, times 100. So you're always going to end up with a percentage. Okay, some percentage value, X percent. So here we got calculate the mass percent for 15 grams of potassium nitrate dissolved in 135 grams of water. Okay. Now, asking you for the mass percent. We don't need to know about moles. This is where things get mixed up sometimes when we talk about the next concentration, which is molarity. There you need molar mass to calculate the number of moles. But here, we're just talking about the mass. And so we're not worried too much about potassium nitrate and what its molar mass is, because we know there's 15 grams of it, which is written here. And then the bottom is the 135 grams for the water plus the 15 grams for the potassium nitrate. We multiply that and we get 10%. Okay, 10%. Now, for example, you may be familiar with this. You may know a saline solution that people use a lot is a 0.09%. That's sodium chloride in water. It's one of those saline solution that if you're in the hospital and they got to give you some liquid, they got to put in a 0.9% sodium chloride solution in you. And we can calculate how much sodium chloride we need. But let's do an example here. Figure this out. And this example here, you're given the mass of the solute and you're given the mass of the water. Okay. There are times that you are not given the mass in the water and we have to calculate it. For example, how many grams of water are needed to make a 5% saline solution with 10 grams of water? Okay. So we set up our equation because we know we're given 10 grams. Okay. We're given 10 grams of sodium chloride in the problem, right there, salt, I should say. And we know that this is going to be a 5% solution. Okay. And so the thing that we don't know is the mass of the water. And so our equation is based on the previous equation it gave you is, the mass of the solute divided by the mass of the solute plus the mass of the water. And so what we got here is an algebraic equation. Now, and we're going to solve for x. Now, you may look a little complicated, and there's a multiple ways to solve for x. This is just going to be one of them, okay? And one method. In algebra, there's a lot of ways to solve for equations, and there's not necessarily a right way to do it, okay? You can attack an algebraic equation multiple ways. And what's important is you get to the answer, okay? How you do it, whether you start to the left, start to the right, totally up to you, whichever you're comfortable. But this is just one way, okay? For example, here's the equation we started off with, and now it's been rewritten. So what do you think they did there? Okay, what do you think they did to go from the equation that was written down to solve for x to this? Well, they multiplied by the unit of 10 plus x on both sides. Okay, 10 plus x on both sides. And so this cancels out this right there. And now I got 100 times 10, which is right there. And then I got 10 plus x times 5.5. Okay. So I just simplified the equation. Okay. That's one way to do it. Some people would take the 100 and just multiply it with 10. You end up with an equation and then take it from there and move things around. It makes no difference how you do it. You're just trying to solve for the x. So now you have this equation and you continue now, and now they got to this point. Well, what did they do here? Well, they simply multiplied 100 times 10. That's all. To give you 1,000. They done nothing on the left-hand side. Okay. Now here, there's a multiple ways you could do. You can multiply 10 times 5 and 5 times X, and then distribute this out. And you have one way to do it. That's one way of doing it. Or you can go this way and end up with this. Well, guess what they did there? Okay, what they did is they divided through by 5, and you ended up with 1,000 divided by 5. Okay. Now the next step would be simply to take 1,000 divided by 5, which is 200. Okay, and now you have 10. You have x 10 plus x equals 200. Now you solve for x, so you got to move the 10 from the left and move it to the right. So you got to subtract 10 from both sides. Okay, so I do a minus 10 over here, and I do a minus 10 over here because these cancel out. Okay, and that ends up as 9 or 1 times 10 to the second. And that's done because of the sig figs, okay? 3 sig figs start off with 5.00%, and that's 190 grams. So what that tells you is that if I take 190 grams of water and 10 grams of salt, I end up with a 5% solution, okay? 5% solution. Now, how do you know that is correct? Well, take that X that you just solved and put it back into the equation. Okay. And put it back up in here and 190 and work it. And you end up with 5.00 equals 5.00. So X at 190 is correct. Okay. Now, the other one, this is the mass percent we just did. Now, you'll find the mass percent used quite a bit out there in the real world. A lot of the wines you talk about when you see the percentage of beer and so forth, those are most of the time the weight volume or volume percentage. But that's how a lot of things are defined as far as how strong they are. You know, it's either weight or weight volume or volume percentage. Now, the next concentration unit is called molarity, and that is defined as moles per liter. Okay, moles per liter. And so what that tells you is this, that if you're given the volume in milliliters, you need to convert that to liters. Okay. Then most of the time you're given the quantity of your solute in grams. And so you need to convert that grams into molar mass. Well, if you need the molar mass, then I need to know the formula, all right? Because I need to write the correct formula to give me the correct molar mass. So that brings us back to where we were writing formulas, okay? So see, it all comes together a little bit. And so let's take this one here. This is calculate the molarity if 9.99 grams of potassium bromide is dissolved in water to make 2.5 liters of solution. Okay. Well, before we do anything, we need to write the formula. We got potassium bromide is what we're given. So we need to write it down. And remember, we were writing formulas down. I always suggested is write them as ions first. We know that potassium is in group 1. The ionic form of potassium would have a +1 charge. It has 1 valence electron. And the bromide would be a -1 because it's in group 7, bromine is. When it becomes an ion, becomes bromide, okay? Hence the term IDE, which tells you you're dealing with the ion. Since it's in group 7, it's going to pick up one electron only. And so its ion has a -1 charge. Now we put these together. That is the correct formula for potassium bromide. Okay. And once we do that, we can look it up and we have the atomic weights for bromide is 79.9 and potassium is 39.10. So I got 18, 19, 6, 10, 11, 119.00 grams per mole. Okay. All right, 119 grams per mole. So we write that's a molar mass. Remember, it's a ratio, and we're looking for moles. So moles is in the numerator. Grams is in the denominator. So we start off with 9.99. Don't truncate anything with respect to sig figs. Wait till you're done with all the math. So carry all the sig figs through in the first step in the moles. And then take all that and divide it through. You're going to end up with 2.55 liters, which is what you're given. And so our molarity is 0.0336 moles per liter. Okay. That means if I took a liter of that solution, it would contain 0.0336 moles of potassium bromide. All right. All right. So anyway, there are a lot of practice. Use the practice sheet to help you work through these problems. If you're having challenge with them, obviously come next Tuesday, come Thursday, following Thursday, bring them to class, and we will definitely go over them, make sure you got them straight, figure out straight. If not, send me an email and I'll see I can talk it through email, whichever works for you. Okay. Now let's do one more. All right. We got sodium phosphate. So sodium phosphate. Okay. First things first, we need to write the formula. We know that sodium is in group 1, so it will have a +1 charge. The phosphate, you might say, where can I get that information? Well, let's direct you to the polyatomic ion table. Okay, it's PO4 -2, -3, excuse me. Okay, and I need to write the formula, so that means I need 3 sodium ions for every phosphate. So I got Na3PO4. Okay. So I got 3 sodiums, 1 phosphorus, and 4 oxygens. And I'm going to have 5 grams of sodium phosphate. And then we're going to take those 5 grams and we're going to dissolve it in 2.55 milliliters. Okay. Remember, molarity is moles per liter. And so we're going to need to convert the milliliters to liters. And what do we know? Conversion factors. That in 1 liter is equal to 1,000 milliliters. Okay. 1,000 milliliters. Okay, so we need 3 sodiums, 1 phosphorus, 4 oxygens to get the formula, the molar mass. And let me stir it up a little bit here. And so when you do that, you end up with 163.94 grams per mole. That is the molar mass of sodium phosphate. Okay. Then we're going to take the 255 milliliters and convert that to liters. And you simply divide it by 1,000. So now we got 255 milliliters converted to liters, and that is 0.0255. And then we go back, input the moles divided by the volume. We end up with a concentration of 0.12 moles per liter. Now you might ask, okay, I got three, let me restate that. You might say, well, wait a minute, I got 3 sig figs here, and I extended my number here to as many digits as my calculator had. But remember, the bottom line is this. Okay, you start off, this is the data that's given to you. You start off with 2 sig figs at 5.0 grams and 3 sig figs. So ultimately, the final answer will be in 2 sig fig formats because that's what you started off with. Okay, though I didn't truncate anything until I was done with all the mathematics at the end. Okay. All right. Now, don't forget the assignments. If you've not done old assignments, you can still go back and do them. You have until, I believe, the 22nd, I believe. Check that, but knock them out. Yes, you get penalized, but some points is better than no points. There's a practice exam on the website. That's a good resource. Also, there's other exams from the previous chapters that we've done. That's a good resource because we take those questions and just apply them to the campus final exam. Very similar. We don't give you the exact same question, but obviously you're going to find different numbers, you know, if I'm doing a calculation. That being said, guys, congratulations. You just finished 15 chapters of chemistry. Okay. In fact, we're ahead. Some department, some classes are a little bit behind. So we got, and my plan was to get ahead so I can have some open days at the end to be open for questions for you. And so it worked out pretty good. All right. Any questions? Any